Okay. Thanks everybody for coming for the Learning Lab 12. Today we're going to be talking about clustering models applied to the energy sector. So I'm going to start sharing my screen and I'm going to start with the presentation. So just for the presentation to keep it nicely, I'm going to just mute my video. So it's not going to be in front of the presentation. I'm going to maximize here. So today, we're going to be talking about clustering models applied to the energy sector. So I'm calling this part one because in 15 days from now, I'm going to be giving the second part because there are several different types of algorithms that we're going to be talking. And I think it would be too much to talk everything in one day. So this lab is hosted by me, Marcelo Guarido, that I'm a data scientist, and I'm the head of the Cruz Data Science Initiative, and it's co-hosted by Daniel Trad, that couldn't come today, that he's an associate professor and chair of the exploration geophysics at the University of Calgary, and David Emery. David?
Good evening or afternoon, everybody, and hopefully you enjoy the lab.
Thank you. You could introduce yourself as well.
So I've been helping out Marcelo for the last year, and I will be an incoming student, hopefully, with Daniel Trad, and joining the rest of you as working away on machine learning.
Yeah, and David has been working with me very closely, and it's been amazing working with him. He was my mentor in Husky Energy, and now I'm happy that I'm able to work with him again. So another thing that I'm going to start talking, it's what I like to call the shameless self-promotion part. I'm going to talk about the Cruz Data Science Initiative. That's a subgroup inside Cruz where we do research, training, and any other stuff related to data science. Uh, what we focus are in data science projects, mostly for in geoscience projects, but could be related to any type of data. We're not close to do uh, any other type of project. And they are both academic and industry projects. Let me just change here for a better view, laser pointer. We also provide some training in R, Python, and MATLAB. That could be programming, could be training in simple programming, as well as some applications, how to apply machine learning, and also to create apps using your codes. And we also provide those learning labs. So if you go and access the Cruz Data Science webpage, that's in the Cruz webpage, cruz.org, and you go to the research link in data science, you're going to see all the information from the previous labs that you can actually watch the previous videos because we recorded the sessions. And we also, all the files that you use for the programming. Now that's finished the self-promotion, let's going to start talking about today's learning lab. So we're going to start with a paper overview. So all the labs this year, you're going to be focusing on some paper, and you're going to use this paper and try to reproduce their methodology. Not all their methodology, because most of those methodologies, they are PhD or master's project. Um, and we are going to try to understand how are their modeling or some interesting parts of their programming part. So today we're going to be talking about one about clustering for seismic velocity analysis. Then we're going to be talking about what is clustering and what are the goals for clustering. Then the Scikit-Learn package, what are the functions that you're going to be using, and you're going to end with a demonstration that's a coding in Python using a notebook. So just to start, the paper that you're going to be talking about today is this machine learning assisted velocity auto-picking from Kenneth Smith in 2017. And what he proposes in his work is to do a semblance auto-picking. So that would be unsupervised learning. And he uses a model named k-means that you're going to explain better later during the code. And he's using k-means by grouping several auto-picking by high amplitude that he does in the semblance, and then get to the cluster centroid of each of the clusters as the picking point. So that's how he works. He creates the semblance, and then he uses a guide velocity that's in this plot here, is this white yellow line, to do some auto-picking that is these blue points. So he just do some auto-picking by high amplitude, and then he groups all those points in here in a cluster. So he's using k-means, and the model or the algorithm is going to do their job. It's going to create clusters in here, and these red points here, they are the center of the clusters, or the centroid. And what he does, he considers that those centers of the clusters are the peaked velocity that it's plotted here as well, the final velocity picking. So for this model, for this work, you need to have some prior knowledge that's this guide velocity, but he could improve it. Probably just one peaked CMP manually, you could use as a guide velocity, and then keep doing the auto picking and use the current picking as the next guide velocity, and so on. And he showed some examples when he do a brute stack, comparing different examples. This one is just using brute velocities, semblance auto-picked without being the machine learning, the AVO auto-picked, and the machine learning auto-picked. And he claims that in the machine learning, as he showed here with these red arrows, that he has a better continuity in the layers and a higher resolution in the final image. So what he claims that the auto-picked velocity using machine learning is better than any other auto-picked methodology. So that's what you're going to be trying to reproduce today, not exactly on the same data set, because we don't have access to these specific data. And sometimes to explain a model, it's easier to just explain with a simpler type of a data set. So for the people that are interested, it's going to be provided this presentation, and that's the paper, and that's the link where you can download it. So that's the DOI. What you're going to be talking now, it's about the clustering models. So what you're going to be using clustering, that's unsupervised learning in the machine learning, you're going to be using to group data points based on similarities. So, and there are different types of algorithms that's going to work that can be divided mostly in three main groups. One are the centroid-based models, where you select a centroid, and then the centroid is going to be moving around to the direction of a high density location of points. You can have distribution-based clustering, like the Gaussian mixture, where you consider different types of distributions. We are not going to be showing this today, but you're going to be showing in the part 2, the distribution-based. And the third one is the density-based, where the clusters are considered by the density of the points. And from the Scikit-Learn library today, the ones that you're going to be checking in the coding are the k-means, that's a centroid-based, and 3 different density-based algorithms: the affinity propagation, the mean shift, and the agglomerative clustering. And during the code, we are going to be explaining how they work. So let's go for the demonstration. So let's code. So I'm just going to leave here the presentation, and that's going to be provided for you as well. So you're going to be providing a Jupyter notebook for you, where you're going to have all the coding that's being used today. So this is a coding provided by me, Daniel, and David Emery. We're going to be studying different models of clustering methods from the Scikit-Learn package. So if you click here to this link, it's going to open the clustering guide for the Scikit-Learn. And here it's going to explain the different algorithms that they have and how to use them, and actually how to use the theoretical explanation for the algorithms that they assume it, and some other examples. And also for the data set that you're going to be using, you're going to be using a toy data set from the Scikit-Learn library as well. If you go to the scikit-learn.dataset, this is a model that have different data sets that you can try. So you just load them and get the data. So the one that you're going to be using today is these load digits that are handwrite digits that initially they were images that are 8 by 8 in pixels that were converted to a data frame by just getting all those 64 pixels and separating different columns. So each column is one of the pixels of 8 by 8 images. That means 64 pixels. If you want to learn more about this data set, this is how you load the data set. It explains everything that you have there. If you want to understand more, you go here to the user guide, and it gives all the explanation. So number of instances, so that's the number of images that we have. That's 1797. Number of attributes, those are the number of pixels, because they were originally images with 8 by 8 pixels. And the range of those pixels, the numbers that you have there, is from 0 to 16. That's something they chose to do. And here, that is the explanation and the original source of the images as well, of the data set. So you can just click here. It's going to show where the Scikit-Learn got the data set. So again, you're going to be dividing in 4 parts. This lab, you're going to be using the k-means, the affinity propagation, the mean shift, and the agglomerative clustering. Just something that I forgot to say previously. Usually, people like to use the Jupyter notebooks in the browser using the Jupyter or the Jupyter Lab. In my case, I like to use the VS Code. So it's just open the notebook here as the Jupyter notebook, but it's just an app. I like to use this program, the VS Code, because I use LaTeX in here, I use HTML, I use Markdown. So a lot of things that I use in my work, I center in here. The only thing that basically I use outside is the R, where I use the RStudio. Another thing that you have to see are the metrics that you're going to be using to measure how the clusterings are doing. One thing that's interesting is that these load digits, we have the class, we have the correct class. I mean, we have the answer. So what we can do, we can use those 2 different metrics, the homogeneity score and the completeness score, to measure how well the clustering is doing. The homogeneity score, it computes the metric by getting each cluster by counting how many classes, or how many, sorry, it's gonna counting for each class or for each answer. In this case, we have the handwriting. So for every number 1 that you know that's a 1, it's gonna counting for each cluster, what's the cluster that appear more to be the consistent one. Because when they do clustering, we don't know which tag represents what. And for the completeness, so it's the opposite. You're going to see all members of a given class are assigned to the same cluster. So how many of the same class are inside that clusters? And both of those metrics assume values from 0 to 1, where 1 is the perfect score. So first, you're going to be using the k-means. K-means is one of the most commonly used clustering algorithms that you're going to find in literature. It's widely used actually in geoscience. And it's a simple but very robust methodology where you start with different centroids. They can be random, or there can be a smart start of the centroids. And then for each one of the centroids and each one of the points, you're going to calculate the distance between them, where we have the centroid and each point. And you're going to group them for the closest one to the centroid. After you finish doing one iteration that, then the centroid is going to be moved to the center of mass, or the average distance of the cluster. And like it's showing here, so the center keeps moving, like this blue one, it starts here, but then it starts moving for each iteration to the center of the cluster, basically, by the density of the points, and also the green, until you have a convergence. So convergence means that the position of the centroid is not moving anymore. It's not changing. And here, in the first part of the code, we're going to just be loading some important packages that you're going to be using. The first one is the NumPy that we're going to be using a lot. From the Scikit-Learn data sets, you're going to be loading the load digits. From the cluster, you're going to be loading the k-means. And here in this line, we are not going to go deep in PCA. This is another unsupervised learning algorithm, but this is used for dimensionality reduction. This is just going to be used to reduce the 64 dimensions that we have in our data set to 2 dimensions, just for plot and see how our clusters are doing. I'm not going to explain PCA today, but in the future, probably in the lab 15, we're going to be talking about dimensionality reduction. Then here, we are loading the metrics and the matplot to make the plots. In this first part here, we are loading the digits, meaning that you're loading the data, and you are separating in X and Y, means that the first data sets are going to be the features, or the 64 columns that represent each one of the pixels, and Y is the label, means if it's the number 0, 1, 2, 3, 4, 5, 6, 7, or 9. Then we are just getting the shape in here and the size, the number of digits that we have, just to make sure. If you run this cell by press Shift Enter or Control Enter, you're going to have the answer here. So the number of digits that we have 10 digits, 0 to 9, the number of samples, that's the number of rows, so 1797, and the number of features, that's 64 features, each one of the pixels. And here, I'm going to start talking about the k-means. If we go to the documentation of the k-means for the Scikit-Learn, you just click here. So we're going to see the explanation of the guide for the k-means. And if you click here, you go to the documentation of the algorithm. So that is an important part. This is a centroid method. So we need to define the number of clusters that you want to separate the data set. And another very important feature, hyperparameter in this model is the init. So how you're going to initialize your centroids. Could be in random position or using the k-means plus. This k-means plus, they say that's a smarter way to initialize. What they do, they just initialize the centroids in a sparse way. So they try to make them distance to each other, trying to get a faster and better convergence to a global minimum. And that's what you're going to be testing for these hyperparameters. So we loaded here all the libraries. So here, that's just the name of the model for the plottings and everything that you're going to be doing in the future. So this is the init. We can select the init or the initializer for the centroids to be the k-means plus or a random initializer. And here, how we do in Scikit-Learn to create a model. We call the model that we loaded here on the top from the Scikit-Learn. We set the hyperparameters that we want to, and then we fit over the data sets. We don't have a target, so the fit is just clustering, just separating the groups between similarity. In most of the classification and the regression, when you fit the data, you have to include the X, the features, and the answer, the target. For clustering, you don't need to. It's just the data, or just the 64 features in this situation. So we train the model here for the k-means. And if you go back to the documentation, after the model is trained, so there are some attributes that you can call from the model. That's the cluster centers. So that's going to be basically the coordinates of the clusters. And what are the labels that you did for each one of the sample? The inertia. So it's just the square distance to the sample to the cluster center, and the number of iterations that we did. Here, in this next part, we are computing the metrics, the homogeneity, and the completeness. And here, we are just plotting how was the answer. So if you run this part and do a Control-Enter, so it's quite fast because the data set is small. And those are the metrics that you get for the homogeneity and the completeness. So remember that 1 is the best possible and 0 is the worst possible. So I got very interesting metrics in here of 0.74 and 0.75. And here, in this next part, I'm going to be plotting the clustering in a 2D plot. Remember that initially we have 64 features. So to plot in a 2D, you're going to be reducing the dimensionality of the data. So that's how we do using the PCA. We're going to set the number of components to 2. So the data that has 64 dimensions is the output is gonna be 2. So we are training a PCA model, and then here we are transforming the data to 2D, basically. So that's the reduced data. And remember that the centroids, they also have 64 coordinates, by the way that you trained here. And what you are doing here, we are just reducing with the same data, with the same model that we fitted over the data to reduce to 2D the cluster center. So that's how we call the cluster centers in the k-means. So the model was trained here, the k-means. We trained it up here. And now we're just using dots and calling the cluster center. So now we have everything in 2D. And here is just the way to plot them. So when you run this, those are the clusters using the k-means ++ initializer. I'm gonna change this to blue. So better red, sorry. So those red X in here, those are the centroids of the clusters. And those are the clusters that were created. So you have 10 clusters, that's the number of digits. And you can see that there is some overlap of the clusters in the points here that you don't see in this example. That happens because initially we did the clustering in 64 dimensions. So when you're doing the reduction of dimensionality to 2D, so that's what's it's happening. So they got a little mixed up. So you can change here the k-means ++ to the random and see what is the difference when you try 2 different initializers. So you see that the metrics got a little worse, not that much. Let's just go back to k-means ++ and remember. So we just reduced it in the third decimal what was the metric, but it's not a big one, a big reduction. But what they claim is that the k-means ++ usually does a better job than the random. So if you plot here, I'm just gonna save this picture here in the VS Code. So I press here. So now the plot is gonna show using the k-means plus plus. And now if I run with the random in here, oops, this one. Now I have the new plot. Just 1 second. Okay. So there are a few questions like, don't we have to scale the features for k-means? Yeah, but not necessarily, depends on how you're doing. Yeah, we're gonna ask Marcel in the end. That's not necessary, that's not mandatory. Maybe you can get a better result if you do from 0 to 1, but this data set, we don't have the features on different scales. So usually you do that to put all the features on the same scale. That's not the case that you have here in our features, because each one of our features represents 1 pixel that goes from 0 to 16. So they all have the same they are all related, they are on the same level, basically. So now if you open this new plot here with the random, so you can just open on the plot. So now we have both and see what is the difference between them. The colors are different because the k-means give different numbers for the cluster. It's kind of a little bit random, but the clusters are basically the same. There are a few points that might be different when you look into the clusters, but in general, they got quite close. We don't see too many difference between them. So that's how you're going to use the k-means. So the most important hyperparameters are the initializer and also the number of iterations. You can change it to more or less. In that case, this data set is not going to change too much in here. So I'm just going to keep the k-means plus plus. So you're going to compare with the others in the end. So the next one that you're going to be talking about, the clustering model, is the affinity propagation. So this is a density algorithm that goes for the center of the data. It doesn't start with any centroid. How it works, it gets 2 points and starts to send message between them. So what they call message, basically they are measuring the similarity between them, called the responsibility and the availability. So the responsibility, that is the accumulated evidence that 1 point k should be the exemplar of I. What mean exemplar? It's one cluster, so it's going to start as basically getting each point as a cluster almost, and then it's going to start clustering them. So each exemplar would be one cluster in lower iterations. In the last iteration, the exemplar is the final cluster, basically. And also the availability, that's the accumulated evidence that Y should choose K as its exemplar. Yes, actually, so the k-means that can have so actually say, I think k-means is sensitive to variance in data, so higher variance, you have more impact on result. I usually use a standard scalar, which normalize the data before putting in k-means. That's true. In that case, you don't have this in this data set because basically what we did, we got a 2D image and just converted it to a 1D array and called each one of the elements as one column. So we are not going to have a problem for this type of data set. So this data set is pre-processed. But yes, when you're using k-means, you have to do a lot of pre-processing. Actually, before doing any kind of machine learning, you have to do a lot of pre-processing before. That's going to be one of the learning labs we're going to be talking in the future, how to do the pre-processing of the data, because it's not just getting the data and throwing through a machine learning model. You have to prepare the data, you have to understand the data, you have to fix the data. Sometimes you're going to have problem. And in the end, when you're going to run your machine learning model, you already spent 80 to 90% of your time just pre-processing the data. And when you do your predictions, you know your data so well that basically you can expect what's going to be the predictions in the end. So yeah, we're not going to be talking about pre-processing today. It's just showing how to use the models. And the affinity propagation, so in the end, after it's going to getting the exemplars, so it's going to getting one of example of the others. So we're going to start have a cluster center in the end. That is just the mean distance between them. And one advantage to use this clustering is that you don't need to know the number of clusters that you want to do. It's going to automatically get the number of clusters for you. In our case, for this data set that you know that you have 10 clusters, is not a good case because we know that you should have 10 classes. And it's very hard to parameterize this model to get to the correct answer. So I actually couldn't. We're going to see here that the results that you're going to get here are not optimized. So that's how you're going to be running. So from the cluster module, you're going to import the affinity propagation. Oh, and sorry, if you click here, again, you go to the explanation here from the Scikit-Learn, how is the computation and how they use, and what are the parameters that are important. One is the dumping, that is just a dumping factor that is just dumping some of the messages they send from one cluster to the other. So they make a difference here. The number of iterations and the convergence iteration. Those are basically the most important ones that you're going to be using. So the convergence iteration is the number of iterations without change to stop the iterations. So if we are in iteration 30 and from 30 to 45 doesn't change anything, so it's going to stop. It's not going to do 200 iterations. So here are some, you do the same way. I'm just calling the name of the model. We call the function in here. We set the hyperparameters. So the same way we did for the k-means. And we fit the data. One important thing that I always set is the random state, because all the random starters, they are not so random. They are pseudo random, that you can get always the same random if you set the random state. So you can reproduce everything that when you get the code for yourself, when you run, you're going to get the same results that I'm getting here. So we are setting the dumping factor, the max number of iterations, the convergence iterations, that all are the default parameters in here. Calculating, again, the matrix, and here, just printing all the metrics, and also the number of clusters that it gets in the end. So if we run this one, it's going to be quite weird, because it got 103 clusters. We know that we have 10 classes, so we should have 10 clusters. And if you look into the metrics, we have this metric for the homogeneity close to 1, but this one very low. So that means that if you get each point as one cluster, basically, the homogeneity is going to be 1. If we get But this number, the completeness, is going to be quite slow. It's going to be 0.3 or something. But if you get all the points as just one cluster, the completeness is going to be 1, but the homogeneity is going to be 0. So what you want is that both of this metric to be good, like the k-means. So this one being high doesn't show so much because this one was low. So we need to check both of those metrics. And if you plot all those cluster centers in here and the clusters, so that's what we have. We have a, oops, let me change again to red. So we have 103 cluster centers. I wasn't able to improve this too much. What I did was to change this number, if I don't remember, 0.98 for the dumping. So it takes longer to run. And that's the example, the number of clusters. Now we just have one cluster, basically. So the completeness got 1 and the homogeneity 0. If you plot this, so we don't have any clusters actually for this one. So gave you an error because you don't have any cluster center. I remember that I did some changes here like this to 20, I guess. And probably increase the number of iterations to 45 or something like that. Yeah. So basically, we could reduce a little bit the number of clusters. We improved a little bit this metric. So we can start playing with these numbers and try to improve this. But I couldn't get something that was reliable for this data set. So we need to be careful when using the affinity propagation. If you go to the Scikit-Learn website about clustering, it tells what's the advantage and disadvantage for each one of the, they'll tell the use cases. For affinity propagation, they suggest to use it when you have many clusters. In our case, we have 10. This is not many clusters. So probably that's why it's not working properly. And the other, that we need to have an even cluster size and non-flat geometry. We have a very good data set. So basically, this is not the recommended model to use for this data set. So another thing, you need to understand your data set so well that you need to understand what's the best model that you're going to be using over it. So we couldn't improve it too much, just a little bit. Now we're going to plot. Now we have 95 centroids, and basically this clustering analysis doesn't make sense. One thing that I tried to do was try to do in 2D. So instead of doing in the 64 original features that we have, I'm going to be doing the PCA. I'm going to use the reduced data that you know that's just a 2D and try to do the cluster over this 2D data in the end. So over this plot, we're going to consider this plot as our data set now. So I did that because I want to see, oh, maybe one of those clusters is way more represented than the others. So maybe most of those clusters are small clusters. But then I plotted the histogram of those clusters, and what we got that they are quite similarly distributed. So there are no small clusters. So now what I'm trying to do here is to using the reduced data that you have just 2 dimensions or 2 features. Those are the hyperparameters that I kept testing and got the best possible. That was still not good. Also just changing the metrics and everything and doing the plot. So when you do this analysis, it's going to take a few seconds. Now we got a little more compatible, more comparable metrics. The number of clusters now was reduced to 31. Sorry, I have to run again because I forgot to change to red. When I did this code initially, I was using a dark theme, so white was good, but now I need to change it to red. And those are the new clusters. So when we try to cluster this 2D data set, so it doesn't make sense as well. If you just save the image in here, if we compare to the k-means, you can see that the clusters, they don't talk to each other when you see these two methodologies. So I would say that the affinity propagation is not a good data model to use for this type of data that we have now. So I'm just trying to remember what I did here. Oh, it just got up. Okay. So now we're going to be talking about the third model today, the mean shift. They say that's a centroid algorithm, but it's a combination of centroid and density. It's because that they start with a lot of centroids in here, a sparse grid of centroids, and then they start to change their position based on the density of the data. So the centroids, they start to move, and the algorithm is gonna do a filter to eliminate very close centroids to not have overlap. So in the end, just gonna consider one centroid as the cluster. So again, you can click here. So that is the explanation. And this is the algorithm that you can use. And basically, the important parameter is the bandwidth. Basically, it's the distance that you want to use to estimate the clusters, or the distance between them. They call the bandwidth. That it's using an RBF kernel. And that's what you're going to be testing in here. So initially, if you set up the bandwidth to be none, it's going to automatically set a number for the bandwidth. And that's how we're going to be loading the function or the algorithm in Shift from the cluster model in the Scikit-Learn. Here, just getting the name of the model for the plots. So the bandwidth, you're going to be setting to none initially. And they're going to be doing all the same coding, calculating all the metrics and doing the plot. So if we do that, it's going to calculate the number of clusters for you as well. So if you set the bandwidth to be none, it's going to say that you have just one cluster. So when you do the plotting, let me already change to red this before. So all the data set is just one cluster. So apparently we have to toy around with the bandwidth. And that's nice because I tried different numbers. Something that I got a good result was this, actually, if I'm not wrong, 29.8. So the number of clusters was 10. And even the metrics, they got a little more stable now compared. You can compare now with the k-means. And when you plot here, so now we have those clusters. We can even compare with the k-means now. So this is the mean shift, and this is the k-means. So we start to have some clusters that are comparable to each other. Again, the colors are going to be different because the name of the clusters are different, but some clusters are quite similar. But there are some changes that are considering this one cluster, where the k-means consider that you have two in here, for example. And some changes in the center here. But for these three on the top right, they are quite similar between these two models. So we were able to use the mean shift for this data set. We can try different numbers just to understand what happens. Well, when I go back, if I select a very small number, like 1 for the bandwidth, what happened? It's going to consider each one of the clusters, each one of the points as one cluster. So that's what happened with the metric. So the homogeneity got 1 and the completeness 0.307. And if you get a very high number, like a 100, we get just one cluster. So we have to toy around. In this case, we know the number of classes. We know that we need to have 10 clusters. So when I did 30 one day, one try, I believe I got 11 or 9. I got 9 clusters. So I did 25. So that's how I got that number, basically. I was trying, so got 57 clusters. So eventually I got to 29.8. So with this bandwidth, I got 10 clusters with the highest metric that I could. And this plot. So now we're gonna, for our last clustering model that's gonna be talked today, is the agglomerative clustering. It's another one that doesn't use a centroid. It's considered to be a density cluster, and it's also a hierarchical clustering. What it does, it's consider initially each one of your points as one cluster, and then start to aggregate these points according to some distance that you can select. That could be the ward average, the complete, or the single, where the ward is it's grouped to clusters in a way to minimize the variance of the clusters that are being merged. The average uses the average distance of each point inside one cluster and then link to the center of the clusters. The complete, or the maximum, uses the maximum distance between all observations of the two data sets. So basically, it's going to group the cluster by the maximum distance they have between them, one border and another border. And the single uses the minimum distance between all observations, or would be the closest part, this one and this one, or very close borders, basically. And it does that until we have just one cluster in the end. So there are two ways for us to set the clusterings. One is to just say that how many clusters we want. So in our case, we want 10 clusters. So it's going to stop the agglomerative process. So how to select, actually is asking a question, how do you choose a clustering algorithm for your data set? Suppose faces predictions. Do you think any algorithm will do better than KNN? Yes, there are some algorithms that are going to do better. Basically, you have to understand how is the separation of your clusters in your data set. If you go here to the Scikit-Learn website, there is this very nice plot in the beginning. So how do you cluster these different type of data set that we have? We have this first one where we have a circular cluster in the middle and another cluster on the border. So the k-means, if you know that you have two clusters in this situation, it's a linear separation between them basically. So it's going to set one point to be a cluster and the other to be another cluster. So it didn't do a good job in this type of a data set, but it does a great job in this type of data and this type of data, basically. K-means is gonna work well if you have the clusters very well defined, basically. When you start to have some mixing, like these both U-shaped clusters, some of the models are going to start to work better. For example, this spectral clustering or this hierarchical one named WARD is going to do better in this situation. But the agglomerative clustering with the single distance is going to do better for this situation and this, but it's not going to work well in this. So that's why you choose by knowing how are the clusters of your data set before. So you need to have prior knowledge of your data set, basically. And that's how you're going to select. And if you go here to the agglomerative clustering that we showed before, and there are basically the same explanation that I put in the notebook. If you go to the algorithms, there are interesting parameters that we can set, the hyperparameters. The first one is the number of clusters that could be none or an integer. So the default is 2 to have 2 clusters. In our case, you can define 10 clusters. Or we can set the type of a linkage to be the word, the complete, the average, and the single, the one that we explained before. And the distance threshold. If you set the number of clusters to be none, then you have to set the distance threshold. That means that what is the maximum distance to stop the agglomeration. So you have to set a distance here that's going to be calculated by a Euclidean distance. And what is the maximum that you're going to stop those agglomerations? So the distance between the clusters that you're going to stop them. Here, I didn't want to work with this distance because, again, I couldn't get to have 10 clusters. So how we set it here, the hyperparameters, is to set the number of clusters to 10 and the distance threshold to be none. If you guys want, you can play around with these numbers. But what you're doing here, we are just changing the type of a leakage. That's the word. That's the way to agglomerate today, basing on the... Okay, see you actually. We can use the word, the complete, the average, or the single. And doing all the same, just computing all the metrics. And you can even see the number of clusters. I just got this one because I was testing the distance threshold, how many clusters it's going to get. In this situation, it's going to be 10. So when you run this, what we got way better metrics for the agglomerative cluster than the k-means. So for this scenario, for this data set, apparently these agglomerative clusters is working better. If you plot now the final clusters, we don't have the cluster center anymore for this type of plot because they were just agglomerating in the 64 dimensions. But you can kind of compare again with the k-means and the others. So this is the agglomerative cluster using the word linkage criteria. So if you compare this with the k-means, we start having still some similar clusters, like these on the top here. Probably they are very well defined clusters, but by the colors, what we noticed that here, basically, we're just going to have one cluster for the agglomerative, just by looking the colors. So actually, it got better to this one. It got closer to this one, to the mean shift. So again, we should have some understanding of the data prior doing our clustering. We can try, again, we can try use different linkage techniques. If you change it here to complete, we just run and thank you. So if you change to the complete, now we reduced our metrics. So remember the complete, what it is doing, It's linked by the maximum distance between two clusters, basically, or 3 or more, depending on the distance. And we reduced our metrics. And actually the clusters start to get quite different. So we can also try the average, that's the distance between the centers of them, of the clusters. So the metrics got a little better in this situation. And even the clusters, it's hard to see, but now apparently we have just 1 cluster here in the top instead of 3. So it keeps changing. So again, you need to have a previous knowledge. And then if you use the single, that's the closest distance between the 2 clusters. So now we basically are getting a terrible prediction. So when you do that, we have basically 1 large cluster, and all the other 9, they are very small clusters. So that doesn't make sense. So basically what got better, that we know the answer was the word. And that's the best metric that we got. So basically, that's what I had to present for today. I'm gonna end up with this thank you slide. And if you have any question, please, now you can ask. You can unmute your mic if you wanna just ask, or you can send a message. Thank you. So I got my video back. So if you have any question.
So Marcelo, did you actually plot, because you know where the clusters are? How do the actual 10 clusters look in the PCA?
I forgot to do that, but I can do now quite fast because we have the labels.
Yeah.
Right? So if we just redo this plot here, but instead of coloring by the labels, we're coloring by the labels from the clustering, by the labels, the data. So those are the original one. So if we compare them now, I'd say the k-means actually got quite closer. If you look to the word, apparently we have 2 clusters here. We have a darker, purple and a blue. So actually, word, yes, we have 3 clusters here. 1, 2, and 3 in the word. But the colors are not so good to see, right? Actually, I think the word is doing the best job. Yeah?
Yep.
So that's the comparison between them. So any other question? So if you don't have any questions, I'm gonna stop sharing and I'm gonna stop the recording. So thank you everybody for joining today. And hopefully I'm gonna see you in 2 weeks. In 2 weeks, we're gonna come with the second part where I'm gonna be explaining other type of algorithms like the DB scan, the optics, the spectrum clustering, and also the Gaussian mixture. So thank you and see you in 2 weeks. Bye-bye.